Welcome to Futures Talks. This interview is brought to you by Imagine, an Institute of Futures Studies at Iqra University, and COMSTECH, the Ministerial Standing Committee on Scientific and Technological Cooperation of the Organization of Islamic Cooperation. We are happy to present an illustrious scientist from an OIC member state, Turkey, and he is joining us today from Ankara. Honorable Professor Dr. ALTUÐ ÖZPİNECİ is a leading and distinguished professor and researcher. He is a professor of physics at the Middle East Technical University, Ankara. His research interests are in hadronic physics, QCD or quantum chromodynamics, some rules, chiral perturbation theory, hadronic molecules, and he has received many awards like the prestigious COMSTECH Awards in 2015. In 2012, he has received an award from Middle East Technical University, and in 2006, he has received an award from Turkish Academy of Sciences, which is GEBIP, which is given to the young scientists of developing countries. Today, we are going to explore his journey, his lived experiences, and we're also going to talk about the accomplishments and the applications of his work on OIC goals, as well as the emerging trends in his field. Thank you, Professor ALTUÐ ÖZPİNECİ, for joining us in Futures Talks today.
Thank you for the nice introduction, and thank you for the invitation. It's a pleasure to be with you tonight.
So, Professor, first of all, we would like to know about yourself, about your journey. What was your childhood like? Where did you get your education? What is your family life? So would you please tell us about that?
Well, my family is, I have parents and I have an elder brother, which I should say that had a significant influence on my education also. Now, I have been always a curious child. When I was small, I used to ask questions. And nowadays, I don't really talk that much. I'm usually known as being somebody who is silent. But then my parents say that when I was a small kid, they just couldn't stop me from asking questions. And then they couldn't answer some of my questions, so they just asked me to go to the encyclopedia and search for it myself. So that was kind of, in a sense, the initial initiation of my journey to science. So I was curious. I was reading encyclopedia, and I was reading whatever I could find. I was interested in mathematics. I was good in numbers, and then I started doing my own experiments at home. So I'm kind of proud that in high school I built my first Van de Graaff generator at home with just everyday stuff that I could obtain at home or in the shops around. And in Turkey, the university entrance examinations, there's a university entrance examination. If you want to go to a university, you have to enter this central examination, and if you receive high enough points, then you can select which department you would like to go. But I didn't know there was any physics department. I mean, I was not aware of the existence of such a department, so I was thinking probably I would be an engineer, either an electronics engineer or computer engineer or a mechanics engineer. But then my brother, when he was entering the examinations, he was trying to learn the possible departments. There were guidebooks describing various departments to the university candidates. And when I was going through that, I saw a physics department. So when I looked at the definition of physics and what the aims of the physicists are, I was like, at the end of my secondary school, I was like, okay, this is what I would like to study. I will study physics. And my brother was going to Middle East Technical University, and I wanted to go to the Middle East Technical University. So that was the moment when I made my decision. Well, the physics for a future career is not really perceived so well because it's not really considered a proper job. So a proper job is an engineering or a doctor or a teacher. So everybody was complaining that I was a successful student. So as a successful student, I should go and become an engineer. So but I was like, no, I will not be an engineer. I will become a physicist. But it was a long time until I entered the university entrance examination. So they almost convinced me that I should study engineering, and as a double major, I should study physics. Now, the university entrance examination is a two-stage exam. So after the first stage, I had a high point. My brother kind of said, okay, so you had these very high points in this exam. Your future as a, whatever you choose is almost guaranteed. If you want to study physics, go and study physics. So then I was, okay, so I gave up. I'm not going to engineering anymore. I'm going to physics. I will study physics. So that is kind of how it started.
And how was your journey, like when you started physics, how has your journey been so far? Are you satisfied being a physicist now, or do you regret
I'm happy
not
to be
doing
a
anything?
physicist. I mean, like just like everyone else, you have ups and downs in life. There have been certain times when I thought that, okay, maybe I should quit. But then I thought, what else I would like to do? Then I would say, no, that this is what I want to do, not anything else.
And who is the inspiring physicist for you among the physicists that we have seen all around the world? Who is your favorite?
Well, this question kind of always arises. I don't, I don't answer this question, to be honest.
Okay.
I'm more interested in ideas.
Okay.
For example, in recent years, especially when I understood it properly, the work done by Kepler, I'm fascinated by it. As a student, I didn't really understand it. Okay, I knew the laws, I studied the laws, I could solve questions, but I couldn't put it in a historical perspective. And so it was just kind of a trivial consequence of Newton. But when I realized that Kepler actually came before Newton, that was when I really became fascinated with him. But again, it's not the Kepler himself, but what he achieved, his achievements, the scientific improvements. And of course, there's all these Newton's dynamics equations. I mean, the achievement compared to considering the time when he achieved it, it's fascinating.
And anything else that you want to share with us regarding your lived journey? I mean, your struggles, personal struggles, anything that.
Especially when I'm talking with students, undergraduate students, one advice I give them is they should try to learn various different topics. I mean, even if they have some topic in their mind that they might want to become a condensed matter physicist, plasma physicist, or etc., they should give a try to the various topics. In my case, okay, in my undergraduate studies, I was more concentrated on particle physics. But then in my undergraduate studies, in my master's, I said, okay, no, I should try something else. I mean, I was kind of bored. Then my master's physics is on condensed matter. And then I said, okay, so I had at least now two different topics to compare. I said, okay, I could actually choose which one I really liked because I knew both sides. And then I said, okay, now particle physics is for me, and my PhD was in particle physics. And since then, I'm working on particle physics.
Thank you, Dr. Aspanjay, for sharing your personal journey with us. And this brings us to the second segment of this interview, which is geared and focused towards your achievements. So you have published many national and international journal papers and conference papers. You have over 33 international journal papers, 4 international conference papers, 3 national conference papers, and you have been part of many scientific and technological research projects. Professor Ospanji, you have numerous scientific contributions. What we would like to hear is that the challenges that you have faced and how did you overcome those?
Well, the first challenge was to study physics, to be honest. So that choice was quite challenging, especially considering all the pressure from my peers and family. But I was kind of determined that I would be a physicist. Now, I'm a theoretical physicist, which is kind of easy in a sense, because in the worst case, if you don't find funds, I mean, you have papers and pen are cheap to find. you can do theoretical physics with just some papers and pen, and with the internet now, you can find any book that you want. Of course, if there is money, unfortunately, doing good science requires funds. So you have to have computers. If you're an experimental physicist, you have to have a good lab. You have to travel. I mean, science cannot be done on your own in your office. You have to interact with other scientists. They challenge their ideas. You should allow them to challenge your ideas so that you can understand even your ideas better. But traveling, again, requires funds. Now, we were kind of lucky for some time in Turkey. There were funding institutions which support the projects that you mentioned. And okay, that was at least I could go around, meet my peer scientists, interact with them, obtain computers which facilitates the computations and the studies I have. That was one of the challenges which I could overcome by such projects. Now, of course, the other challenge is education part. I mean, I'm also not just a researcher, but also I educate new students, and hopefully they become scientists. And that also requires time. And in fact, if anybody would ask me whether I enjoy teaching more or doing research more, by a very small margin, I would still say teaching is, I find teaching a bit more enjoyable than doing research itself. Both are enjoyable. And of course, teaching takes time. You have to create the resources, especially in countries where the English is not the national language. The resources in written in national language are scarce usually. This is also true in Turkish. I'm also trying to create some resources in Turkish for the Turkish students, not just my own thesis students, but also students in other universities.
So, Professor Özpenci, my question was it your conscious decision to take up theoretical physics instead of experimental physics, because you knew the funding would be an issue if you were to choose to become an experimental physicist?
Well, I believe that one should follow their dreams, what they enjoy doing. They should try to do that. The other problems, I mean, if there are problems on your way, you will find ways going around them, overcoming those problems. When I first wanted to do physics, when I was before university, in fact, I was more interested in doing experiments to understand how things work. And well, as a kid, whenever I could get some old radio, I would open it up, try to understand how it works, and if it's not working, try to fix it. But then I was more curious about how the various parts in the radio work. So I started even before university. In high school, I started reading about condensed matter, the semiconductors, the p-n junctions, etc. But then I was more curious about, okay, how the atoms work. And when you start asking how the atoms work, then you go to how the nuclei work and how the subatomic particles work. So then I was more interested in the particle physics. And at that time, I also came across a book by Weinberg, The First 3 Minutes of the Universe. It was a book in my high school library. I was also fascinated by that. So when I came to university, I was planning to study either cosmology or particle physics. So at that time, I didn't know about the other problems with the fundings, etc. But as I said, I still think that I had the correct decision, not because it's easier to do theoretical physics, but mainly because that is what I enjoy to do.
Okay. So Professor Özpenci, can you please share some of the researches and the projects that you have done?
Now, my research is specialized on what we call hadronic physics. We are trying to understand the properties of hadrons. Okay, so what are the hadrons? If you imagine the atom, they are made up of nuclei and the electron, and the nuclei is made up of protons and neutrons. Protons and neutrons are just two of the hadrons that we know. They are made up of particles that we call the quarks. The proton is made up of 2 up quarks, 1 d quark, and the neutron is made up of 2 d quarks and 1 up quark. So now we have all these quarks interacting with each other and forming the proton and neutron, and in turn, they just form everything that we see around us. But the question is, what other structures do these quarks can form? Like, do we only have the proton and neutron? Well, like accelerator experiments tell us that there are hundreds or if not thousands of other hadrons formed by quarks. And it's not just we have 2 quarks, we have 6 quarks in total, and 5 of them can actually form the hadron. The 6th one decays so fast it cannot actually form a hadron. So up until recently, until like 15 years ago, all the hadrons that we had seen were either like proton and neutron, in the sense that they had 3 quarks, or like what we call the pions, 1 quark and 1 antiquark coming together and forming the hadron. But at the beginning of 2000, we started to observe some particles which, we had some difficulty explaining them in terms of quark-antiquark pairs or 3 quark systems. So now the question is, what are they? Some proposals are maybe they are just molecules, meaning that in a sense just like the nuclei, but they are not made up of protons or neutrons, but other hadrons. They might be such nuclei-like structures made from other hadrons. They might be, instead of a quark and an antiquark, they might be systems that contain 2 quarks and 2 antiquarks, or 4 quarks, 1 antiquark, a 5-quark system, so-called the pentaquarks. We don't really know yet. There are some indications that we have tetraquarks, pentaquarks, but the one challenge over here is, how do you tell that one particle is a pentaquark or not, or a tetraquark or not, meaning made up of 4 quarks, 2 quarks, 2 antiquarks? If you imagine what we see in experiments, we see all these particles, but we see their momentum, their charge, a few of the other properties, and how they decay. So how can you tell, just by looking at these, that a particle that we see in the experiment has 2 quarks, or 1 quark, 1 antiquark, or 2 quark and 2 antiquark? How can we differentiate them? There might be even more exotic possibilities that is allowed by quantum mechanics, especially one particle that I am studying we are asking the question, is it possible that this particle is at the same time both a quark and antiquark, and 2 quarks and 2 antiquarks? Is possible that it's a superposition. And we had also developed with my students a model that will allow us to study such a system. But unfortunately, at the moment we don't have enough experimental data to really distinguish these 2 cases. And we are waiting for new experimental data.
Okay. That is very interesting, and talking about physics and talking about particle physics, what's happening today in the world of physics is very interesting. There are a number of different theories going around. Even a layman like me is very interested in what you guys are thinking, and how do I make sense of this world, which can be made of quark and anti-quark together at the same time. So it's very interesting concept, sir. I would like to know, Einstein said that he is an artist and he works with his imagination. So I was wondering, what is the role of imagination in your scientific work?
Well, that's a tough question. What's the role of imagination? Well, there are many things that we need to do. In science, what we are trying to find is coming up with new methods that would allow us to understand what we see around us, make sense of the theories we have, make sense of the experimental results that we obtain. Now, the imagination, what I understand from imagination is essentially to think of things that don't actually exist. But at the end of the day, that is what we are trying to do. So especially in fundamental science, let's say if you just release an apple, we know what will happen to it. There's not imagination there. But if you start colliding quarks, or if you come up with a theory which describes objects that we have never seen and we will never be able to see with our eyes, Now that needs imagination. Without imagination, you cannot actually, without imagining what is going on there, you cannot actually do anything. That is probably one thing that most students find difficult about physics, because quite often we talk about some abstract concepts which we cannot see around us.
And now that we are also talking about consciousness in science, it is something which has baffled many scientists before, because they thought that they can only work on those things which are observable or which we can know through our senses. And consciousness, so once again, was not is not within their domain. So when they bring in consciousness in physics, for instance, how does the paradigm of physics change?
Well, the problem of consciousness, okay, we have this sense about consciousness. So when we say that, when we talk, we use this word consciousness, but when it comes to defining it, we have difficulty defining it. So even being a concept which is hard to define, how can we determine how will it fit in physics? I don't really know. There's another related concept of free will. So do we have free will or not? I don't know. As a person which has the weaknesses, let's say, I would like to believe that I have a consciousness, and I also have free will. But when I look at the things that I study, the things that I know, the theories we have, I don't see a place for them.
Okay.
But, well, I don't know how things will evolve.
Okay.
But at least we should first understand what do we, when we say consciousness, what do we really mean by that?
Okay, so the definition is still the problem. And that's what you think, that unless we are able to define it and define it in a way where we can study it using scientific methods, uh, unless we do that, we cannot talk about it. Is this your position, Professor?
Yes, in a sense. You see, for example, if you look at from the Newton's mechanics, well, Newton's mechanics tells us that if you know the forces acting on the system, if you know the at a given point the position and the velocity at a given point, at a given time, then you know what the system will do at a later time. Well, that includes all the atoms in our body, in our brains, whether I will raise my hand or not. Those are all determined. Well, quantum mechanics kind of challenged it in a way, in a sense, in the sense that we cannot really know position and momentum at the same time, and the outcome of experiments turns out to be probabilistic. But still, quantum mechanics is quite a deterministic theory in its own, if you leave aside the measurement problem. So if you look at it from this perspective, given enough technology, we can actually predict what you will do, what I will do, I don't know, in an hour. But
So even on the particle physics, like when you're doing quantum physics, it is, you saying that it is predictable, it is determined?
In this sense, it is determined. So, for example, if I create a pion in a collision, let's say it's one of the mesons we have, one of the hadrons we have, I don't really know when it will decay. These pions, they are unstable particles, and they decay. They can decay, in fact, quite fast. In a millionth of a second, they just decay. If you give me one of them, I don't know how, if it will decay in 1 over 10 to the 22nd, or whether it will live 1 year. I don't really know. In that sense, it's not really deterministic. But if you give me 1 million pions, I know how much of them will remain in 1 over 1 millionth of a second.
I see. So the larger bodies can be predicted. Is that what it is? Like when we talk about particle physics, we say that on that level, things are not are at best probabilistic. They are not certain. But when we talk about the big bodies like sun and other planets, we can predict them. So as you said, like if we have one pile, you have difficulty predicting about it. But if you have millions of those, you can. So is that a similar thing?
In a sense, you see, this is what we call the Copenhagen interpretation.
Okay.
But still, even there are certain difficulties in the sense that, for example, in this description, I'm saying that, okay, there is the pion, which I have to treat quantum mechanically. There's also myself, or the measuring devices, which I shouldn't treat quantum mechanically. So I make such a separation. Is this valid? We don't really know. Because if that is not valid, so the uncertainty in the Copenhagen interpretation is mainly in the measurement problem. So if this is not valid, if you take the pion and yourself both as a quantum mechanical system, then how that system changes, there's no probability there. It's highly deterministic.
Okay.
So then there is the question, how does our perception of the world around us emerge? That is still not clear.
And we also talk about things like, we hear physicists talking about dark matter, dark energy, and then when we probe into it, we find out that these are mathematical abstractions, and you need to have these elements, otherwise you cannot make the equation work. Uh, would you like to comment on that?
Well, you see, these dark things, let me call them. So because usually we make measurements, and in our measurements, we seem to see some effects whose cause we don't seem to be observing. Like, what is this dark matter is essentially we propose this dark matter because when we look at galaxies and how they rotate around their centers, when we look at the stars rotating in the galaxies, we see that they are rotating very fast, much faster than we would have expected from the visible galaxy. So just imagine you are taking a curve, but with a very large speed. If your speed is very large, you will not be able to stay on the road. But somehow these stars seem to be rotating around their galaxies. So we say that there is something else that we cannot see that is pulling these stars so that they can rotate so fast. Okay, so here there's a concrete observation. On one hand, we see the stars, we can estimate their masses. So we can estimate how much they pull the other rotating star. On the other hand, we can measure the speed of this rotating star, how fast it rotates around its galaxy. And from our understanding of how nature works, you see, our understanding is based on our experiments done on Earth. From our understanding, there's a missing piece over there. We don't really know what is the missing piece. If you ask a particle physicist, they will say that there is dark matter over there. If you ask a gravitational physicist, they will say, okay, the gravity behaves differently at such large scales. There's no additional matter over there. And if you ask an astronomer, they will say that there are invisible, because they are not emitting light, invisible planets and spent stars over there that we cannot see, which is creating this additional attraction. We don't really know. So that is still, we are looking for experiments. Experimentation will eventually tell us. Of course, for particle physicists, the interesting thing is if there are new particles that we couldn't observe on Earth yet, because that will open some new research paths, some new understanding on how the universe, how the nature actually works. Sorry.
I have to move to the next segment, but I would love to ask you one more question regarding the Nobel Prize in physics this year was given to a theory which comes up with a revolutionary idea that there was not only one Big Bang, this Big Bang is continuous. How does it change the paradigm of physics?
Well, you see, that is one of the theories of the Nobel laureate. But as I said, it's a theory. We don't really know whether it is correct or not. The opponents of this idea of a repetitive universe is that one problem we have is entropy should always increase. But if you have a repetitive universe, that is, you have a Big Bang, then the universe stops, it contracts again, there's a big crunch, but then it bounces back again. This is what we call the cyclic universe model. But if you have more than one beginning, they should all start from a low entropy state, which is kind of how the entropy increases, how does it decrease? So that is one question that this model should explain. Another problem with these models is, especially you mentioned about dark energy. So we propose that there is this dark energy mainly because, again, when we look at the universe around us, what we expected first was, okay, Hubble made the observation that the universe was expanding. But there is gravitational attraction. So due to gravitational attraction, what we expected was, okay, it's expanding, it should slow down. It should slow. How much it will slow down? Well, we don't know, depending on what is its initial velocity. So it might keep on expanding, or if it is not moving fast enough, it will slow down and it will collapse. But recent experimental observations show that the universe is not slowing down. So if it is not slowing down, then we will not get a crunch. The universe will not stop and contract again. So I would say that those theories are still are currently in trouble.
Okay. Okay, Professor, that brings us to our third segment. And here we talk about the application of your work on completion of OIC goals or their action plan, which ranges from peace and security to combating climate change, overcoming sustainable development challenges, alleviating poverty, overcoming diseases and health problems. And our growing understanding is that research and development are the key components for creating a sustainable, equitable, and humane world. And you have worked on safe nuclear energy, and green energy can substantially increase environmental sustainability. A major environmental concern related to nuclear power is the creation of radioactive waste that can remain radioactive and dangerous to human health for thousands of years. You have attended one workshop in NATO in 2008 at Yalta, Ukraine, where the workshop was on safe nuclear energy. So, what is your opinion on how nuclear physics can help to make a sustainable, equitable, and humane world?
Well, let me take your question with a broader understanding, if you don't mind. Now, one question that is quite often asked, especially to theoretical particle physicists, is what is the use of your work? How will it be applied? I used to try to come up with various applications until I came up to a defense of one of the founders of Fermilab, which is one of the big accelerated particle laboratories in the US. So I think it was after the Second World War, this founder, I forgot the name now, he was taken to court because I think he was accused of treason to the country. And the question was, okay, they were asking many things to him, asking him to explain why he spent so much money in this particle and nuclear research. And they were asking him, okay, whether his research, at that time, it was one of the, close to the world wars, it was, the hot topic was defense. So what is the position of the research in the defense of the country? What use does it have in the defense of the country? And his answer really shocked me when I first read about him. He said that, okay, the research I do has nothing to do with the defense of the country, but the research I do makes this country worth defending. So quite often we talk about the pride of being a human being, but then the question is, what is this pride in? I would say that the two things that we should be really proud of as human beings that other living beings cannot do, but we can do, is that we can do science. We can understand the universe, not just what is happening around us. We can understand the universe. The second thing is art. So I think that these two things, for being able to do these two things, we should be proud of being a human. Okay, let's come to the application part. Now, not my active research, but I should say that one possibility that is really exciting me is in nuclear physics and nuclear research is not really energy, but rather health. In the sense that, for example, I hope nobody will need them often, but if you want to find an MR, if you want to have your MR taken or computerized tomography taken, those were basically our detectors of particle physicists, something like 50 years ago. Or if you want to have a PET scan, there you are using antiparticles. Another possibility that seems to be evolving at the moment is so-called hadron therapy. There are many centers in Europe and in around the world, let's say, that are doing hadron therapy, which is a treatment for cancer patients. And for example, if you know about radiotherapy, in radiotherapy, what they do is they just radiate you with gamma rays. But the problem with gamma rays is that when they touch your skin, they give energy to your skin and they damage all the tissue that they go through. But instead of using gamma rays, for example, you can use protons or helium nuclei or even carbon nuclei. The nice thing about these hadrons is that when they enter your body, they don't damage the tissue as they are going through your body until their energy drops to some critical value. When the energy drops to some critical value, they just explode. They release all their energy and killing the tissue around them. So what is done in hadron therapy is that the energy of these hadrons are adjusted so that they will create damage only when they reach the depth where the tumor or the cancer is. So they don't damage the nearby tissue, they only damage the cancerous tissue. So that is a health application which really excites me.
The next question is, how do you think we can increase collaboration and cooperation among scientists of OIC member states to fulfill the OIC action plan that we mentioned earlier?
Well, cooperation, scientific achievement, whatever it is, it can be due to cooperation, papers, or whatever you want, is proportional to how much you spend, unfortunately. So you have to spend in order to obtain some achievements. Without spending, that's not possible. So in case we can find funds to support various scientists, you see, the scientists are already very much interested in cooperation. As a community, they have to cooperate. But to cooperate, I mean, you cannot cooperate with others just from your office. You have to go, you have to organize conferences, you have to organize meetings, joint work, joint projects. But at the same time, unfortunately, scientists, for example, if you take my example, I became a scientist mainly because I wanted to understand how nature works. But organizing a conference has lots of bureaucracy. So there should be all this support staff supporting scientists when they do their organizations. So I don't know if you know about this International Center of Theoretical Physics, for example, in Trieste, Italy. There they organize lots of conferences, inviting people from especially developing countries, including OIC countries, but all the bureaucracy is done by the institute. I don't know such a institute in OIC countries, for example. The OIC countries usually lack all these research institutes that we see in, I don't know, in European countries or in the US.
So is it only the organization of conferences that would do the trick, or we need funds to have better labs, to have set up those kind of equipments that we require to create science?
Sure, all of them. We need to have centers. That is one thing that I see is missing. There are very few centers in OIC countries. Centers where there will be doing some research, like the accelerate the CERN. If you take the CERN as an example, it's a lab where thousands of scientists from all around the world from every country is coming together and doing research, doing science, and collaborating for a common purpose. We lack such a facility. There is Sesame, but even that is quite limited. We should have more examples of such facilities. Of course, when you have such centers, the conference and those centers become also centers for uniting, coming together for conferences, for doing scientific research, etc. But I will repeat, such centers also require funding.
Okay, Professor Aspanji, the next question is about the emerging trends in your field. What are the emerging trends? Where are we going in theoretical physics?
Okay, in hadronic physics, let me start from a very smaller topic. From hadronic physics, I say that a quite large interest currently is in understanding the so-called exotic hadrons. We have 4 quark states, 5 quark states, and well, we think that we have. How can we understand that? QCD is itself a problem. I have been talking about these quarks, but nobody has observed a single quark. So we say that the quarks and gluons are confined inside hadrons, but we don't know whether QCD predicts confinement or not. It's still not resolved. And this is one of the, in fact, $1 million problems. Whoever solved the problem of confinement will receive $1 million. And if you go to a more theoretical physics, one topic that is really exciting me, especially in recent years, is gravity. And there are all these new observations. You see, one problem with gravity, we haven't been able to write the quantum theory of gravity. There's no quantum theory of gravity. If we try to write, for example, if you look at electromagnetism, we have a quantum theory of electromagnetism. If you do the same thing to gravity, the theory you obtain just doesn't make any sense. So, and we don't really know how to quantize gravity. Now, one of the problems with gravity is we don't really have lots of experiments doing gravity, because gravity is so weak, we cannot measure it in our accelerators. The place where quantum effects will be important and gravity will be important will be black holes. But black holes, until recently, we couldn't observe them. But now we can observe gravitational waves, we can observe colliding black holes, we even could take the photograph of a black hole. Now I'm expecting significant developments in the next few decades, let's say, on our understanding of gravity.
And in the OIC member states, you said that we need more collaboration, we need funding to organize conferences, partnerships, as well as to establish a place where we can experiment, maybe something like CERN, and it will definitely need lots of money. But right now, most of the OIC member state scientists have to go to the developed Western world in order to do to achieve any kind of greatness, if they have to do any kind of experimentation. Whereas when we started off, you said that in theoretical physics, you only need a pencil and paper, and you do not need to do that kind of experimentation. So do you see more physicists in the OIC member states who are doing theoretical physics for this reason? And do you see some great names as yourself in the OIC member states?
Well, you see, one should probably make a distinction between surviving and thriving, living up to your potential. I can survive with a paper and pencil, but I cannot thrive with a paper and pencil. I cannot live up to all my potential with paper and pencil. So, unfortunately, including my country, we are mainly trying to survive, not really thrive, which I see that it's a similar problem with other OIC countries. When you go to developed countries, you see that they are thriving. I mean, when we were chatting before the program, you were mentioning that we have all these brilliant students, which we are having problem with the language, finding sufficient resources, etc. It's not a problem of whether okay, we are we have a less potential or more potential than the scientists in the developed countries. It's more of a problem of what is given to us so that we can produce collaboration wise or scientifically. So when I look at my colleagues in Europe, in the States, and when I compare it with the things that I have to deal with in Turkey, I see a huge difference. Now, this ICTP I was mentioning, I was there for 3 years as a postdoc. For example, one of the visions of ICTP was to bring scientists from the developed worlds, from Europe, from other technologically and scientifically developed world, and the developing and underdeveloped countries, like the African countries, the East Asian countries, etc., and to bring them together so they can do science together. So I think that was a perfect motivation. Such centers, that I think they are now increasing the number of such centers, but even within OIC countries, I believe we should have such centers. I mean, if you want to increase cooperation, we have to first get to know each other.
Absolutely.
And as a physicist, I would like to go to a place which will help me be a better physicist. So at the moment, it's in the developed countries. So we should also have incentives to bring the scientists to such places. Like ICTP organizes this International Center for Theoretical Physicists, organizes summer schools and conferences, bringing down scientists from developed countries. And so if you have such centers, and if they have enough funding, they can also bring them. In that case, scientists from OIC would also be interested in going there.
Thank you, Professor Ospanji. If I have missed anything, or if you want to add anything that you like, that you want our audiences to know, please feel free.
Well, one thing that we have been dealing with recently is performance. So even in the universities, we have to measure the performance of scientists in order to promote them or encourage them, etc. Now, one thing I have been thinking recently is, on one hand, we are interested in making progress, making more papers and making more contribution to science, etc. This is what we call the outcome. Now, there is also, this outcome would depend on two things: the efficiency of the scientist that is creating these outcomes, and the input. So what do we give to these scientists? I don't believe that the efficiency of scientists in OIC countries is any less than any developed country, probably even more. But the problems that we are usually facing is with the input. So just to give an example from Turkey, the project funds that we can receive from the funding agencies compared to the funds that my colleague in Europe can receive from their funding agencies is almost negligible. So this in that sense, funding is, I find, it's really the biggest problem over here.
Thank you so much, Honorable Professor Dr. ALTUÐ ÖZPİNECİ. We salute you for your service to humanity and science. Thank you very much, sir.
Thank you for inviting me again.
Thank you very much for joining us in Futures Talks today. We had a wonderful discussion with Honorable Professor Dr. ALTUÐ ÖZPİNECİ, and in the next episode, we will bring another leading scientist from OIC member state. Till then, stay tuned and be well.